Oh no. No, 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 no. Uh-oh. Okay. No worries. Okay, here we go. Today we are going to talk about logarithms. Why do you make that face and that sound? They are wonderful, wonderful equations. Okay? A logarithm. First of all, what's inside must be positive. The base must be positive and not 1. We're going to fill in the definition here shortly. Okay, so y equals log base a of x if and only if. Say no. Okay, log base a of x equals y if and only if base a raised to the y power equals x. Definition of a logarithm.
Logarithms aren't that hard. I mean,
Gotta be used to them. Okay. Now, we are going to practice rewriting back and forth. Okay? Because if you can't rewrite back and forth, you're not going to be able to do a lot of things that are going to be happening in this chapter. All right? So,
oh well, guess we can't learn today.
we will learn. Don't you worry. This happened. This happened last hour, or first hour as well. Okay. Not a problem. Oh, you know what? Let me try one more thing. Okay. Whoops. All right, here we go. Log base 2 of 16 equals 4.
We didn't even say
Log-
if and only if. What was it?
Yeah.
Log a of x if and only if. Oh shoot.
Okay, log base 2 of 16. If we are going to rewrite this, what is the base?
2.
And then we circle around to the 4 is the exponent equals 16. Log base 10 of 10 equals 1. Here's our base. Exponent equals what's inside? 10. 10 to the first equals 10.
Interesting.
All right, we're going to skip the next logarithm. I think we're getting the picture here. Let's talk about going the other way. We know that 2 to the 4th equals 16.
The log 216 equals 4.
Okay, good. Whatever is our base stays as our base. So we have log base 2 of 16 equals the exponent of 4. Okay, a logarithm is an exponent. Okay. 5 to the 0 equals 1.
Yep.
Okay. Log, everybody together, what is the base?
5
Of
1
equals 0. The exponent is 0, so the logarithm equals 0 to the equation.
What is that called, the 1? Like 5 is the base and 1 is the what?
1 is what's inside the logarithm.
What's that called in the
It's the domain, I guess you could say.
Oh.
Okay. All right. Let's talk about some properties. Okay. Properties of logarithms. There are 4 of them. These will help you. They'll make your life a little bit nicer if you can apply them to simplify. Okay, if you can understand how they work and be able to simplify them, they will save you some time in the long run. Okay, so log base A of 1 would equal what?
A.
Colby, why did you say 0?
Oh, gosh.
Okay, so if we rewrite this, base A to the 0 equals 1, anything to the 0 power equals 1. So when you see log of any base with a 1 inside, bam, you know it's 0. Okay, that can save you some time. Log base A of A, write it down. Think about what you would evaluate it to be. Log base A of A, what do you think? 1. Why is it 1? Our base is A. We raise it to the first power and get A. A to the first power equals A. Okay. A logarithm is basically asking, here's your base, what's the exponent that'll give us what's the side? Okay. All right, log base A of A to the x.
Oh, my ears. Oh, is equal to
Okay. Zach seems unsure. What do you think?
It's X. Oh, got him.
So A to the X equals A to the X, right? A to this mystery power equals A to the X. Which can be helpful if you are simplifying expressions that involve logarithms.
Wait, so, like, are we gonna do, like, polynomials with logarithms?
No. Very separate.
They're what?
They're separate. Okay. Our last one, if log base A of x equals log base A of y. If log base A of x equals log base A of y. What would be true? Okay, x equals y would then be true. Okay, if two logarithms that have the same base are equal, then what's inside must be equal. Okay, just like our example yesterday with like 2 to the 3x plus 3 equals 2 to the 5x or whatever that happened to be. As long as the bases are the same, then we can use what's inside for equality. Okay, so what I'm going to do is I'm going to put up 4 expressions that I would like you to simplify. I would like you to work with your neighbor to come up with 4 answers that you think make sense. I'll give you about a minute to do so.
I had to whip out the old calculator.
No, this is by hand.
With a calculator in that.
Nope. Nope. You can do it.
Would that, so they're supposed to know. So they're going to tell me. They're reading my calculator. Would it be 2 the first one? Because the next one is 0. What? How does that work? It's weird when you put your tongue on this wall, you know, like a little wall, you can like feel the electricity. You know, it doesn't hurt like a distinction. I just had something else on like that wall with a little wall. It doesn't hurt, but it feels like it's like a some spice on it. So is it weird? Interesting. What is that? If you find 9 break off the calculator. Can you explain the third one?
All right, let's come out together. Part 1, what do you have for the first one? Anybody from part 1? 4 squared equals 16, so this logarithm is 2. Very good. Pod 2, what do you think about log base 5 of 1? 0. Good. 5 to the 0 power would be 1, so log base 5 of 1 is 0. Okay, pod 5, what do you think about the third one? 1/2. Let's rewrite this one. 9 to the 1/2 power equals 3. Is that a true statement?
Yeah, because the square root, not 1/2, is like a square root.
1/2 means square root. Okay, remember our fraction? Those our fractional powers are specifying roots. So if 1/2 is our exponent, that means square root. Square root of 9 is 3. Okay. Pod 6. What do you think about the fourth one? Not sure. Would you like to phone a pod?
Phone me. Phone? Yes.
Zach, do you have an answer for it? Zach.
Shoot, I actually forgot what. It was gonna be like -0 or something.
-0. Okay. We're gonna write undefined. Okay, let's go back to the definition. What is inside our logarithm is always positive.
Oh, weird.
If you were to try to plug this into your calculator, you would get a domain error because the domain of a logarithmic function, which we'll talk about here soon, is 0 to infinity. Okay? We can't have negative numbers or even 0 inside of our logarithm, otherwise it's going to be an undefined value. Okay? Good job.
Wait, what do you mean it's going to come in undefined? If you type in log.
If you type a negative number inside of your logarithm, it'll give you an error in your calculator.
I got 2.85 times I. Is that wrong, or is that just too advanced?
Well, your calculator does things a little bit differently than the rest.
Well, no, I did log base 3.
I understand. I understand that. So your calculator is just a little bit more high-tech.
Is that right? Technically?
I mean, yes, but we're not going to express it that way. Okay, it's imaginary. All right, yesterday we talked about the number e. I want to talk about what it looks like inside of a logarithm. I know this is not new information to you, but yesterday we called it the natural base, right? So inside of a logarithm, we call it the natural logarithm. And instead of writing log base e, we write ln. Okay?
It looks like it says Loge.
Okay, I do want you to practice doing some rewriting with these, even though e is irrational, right? And so the number is going to go on forever.
What was that?
If you see the natural log, we know, or I need you to know that that means log base e, okay? So we'd have e to the 2.302 power is approximately 10.
Wait, I thought it was 10 to the 2.302 power.
Nope, it's whatever the base is. And since our base is
Oh,
e,
okay.
we have to keep it as the base for the exponent. Okay. How about the other way? E squared is 7.3890. Okay. If I want you to put that into logarithmic form, Cole, do you have a question?
No.
Okay. Since our base is e, we have log base e, or natural log, of 7.389 equals our exponent of 2.
Why did they feel like, well, what does LN stand for?
Natural log.
But
But you guys have to keep in mind that math was not invented in the English language. And
it's like
so
log natural or something.
I don't know exactly what I mean, that's not what I want to focus on right now, but it wasn't in the English. Okay. All right, let's talk about these two functions.
Where did Euler's number come from?
Not a conversation for right now. Y equals 2 to the x and y equals log base 2 of x. What do we know about those two equations specifically? Two to the x and log base 2 of x. They are inverses of each other. Okay? These two are inverses of each other, which we are going to use that relationship to come up with our parent graph and any other parent graph that we talk about with logarithms. Okay? So, let's remember what we know about inverses. If we are finding an inverse, what is the basic way to describe any process? Switch x and y, okay? So, if we have the coordinate of -1, 1/2 on our 2 to the x graph, right, this is -1, 1/2, then on our logarithmic graph, it's the coordinate 1/2, -1. -1. Okay. On our exponential function, we have the coordinate 0, 1. So on our inverse, it becomes 1, 0. And last but not least, the 3 points that we like to talk about, this coordinate on our exponential graph is 1, 2. So that becomes 2, 1. our logarithmic graph?
Wait, I just noticed. Actually, I'm not sure.
Okay. Do you see the reflection? About what line?
X equals
Y equals X.
Oop, that's-
Okay. So what's that going to mean about our asymptote? It's going to be the same?
No, you said slant.
Slant. Well, let's think about it. If we have Y equals X, and we take this and we reflect it over, well, that's what we're reflecting it over, right? And so, well, I mean, you're seeing the symmetry. You're doing a good job seeing that symmetry. But what's going to happen to the asymptote? It's no longer going to be horizontal. It's going to be, it's not going to be slant. That's what we are reflecting it about. It's going to be vertical. X equals 0 is going to be the asymptote for our parent function of a logarithmic graph. Okay. So I want to start from scratch. I want to build a parent function for log base 3, and I want us to think about some of the relationships that are happening. Okay. I'm going to go back to log base 2 very quickly. If I were to make an XY table out of these coordinates right here, what do you notice about those coordinates? They're flipped, right? We need to use that relationship to help us when we build our other logarithmic graphs. Okay? So back to log base 3 of x. Okay? Just like with exponential functions, I want us to consider the parent function and then transform it from there, however we need to. Okay? However, since we're talking about logarithms, which are inverses to exponential functions, I still want you to consider negative 1, 0, 1, but now where will negative 1, 0, 1 be? In the y column.
Wait.
What do you mean consider? What do you mean? Well, what do you mean you need to consider 0, 1?
Well, I always ask you to plug in negative 1, 0, and 1.
Oh, okay.
But since we're doing logarithms, I want you to do it in the y column. Okay?
And then like do it backwards?
Since they're inverses, it's gonna look backwards. Yes. So when we have negative 1 for y, 3 to the first power is 1/3. That's what our x value would
So
be.
you want us to do it backwards where we solve for x instead of solving for y.
Yes. Okay. If our y is 0, 3 to the 0 is 1. If our y is 1, 3 to the first is 3. So you're going to notice a pattern, right? It's the same coordinates we were talking about yesterday, but they are just inverses now. Okay, the x's and y's are switching. Okay. So what we're going to have, parent function will have a vertical asymptote of x equals 0. Okay, and then we have 1/3 negative 1, 1, 0, and 3, 1.
How do you know how do you know your asymptote is 0?
Okay, the parent function is going to have asymptote at x equals 0, and then if there's any sort of shift horizontally, it's going to move with that shift, which we'll see here in a moment. Okay? Now, you know I'm always going to ask about domain and range. Okay? Remember, domain and range switch just like x and y. So, what is the range of any logarithmic function?
0 to
All real numbers, because the domain of any exponential function is all real numbers. Sorry, I changed my one time. Okay. All right, now what about our domain? Tanner, what would you say about the domain?
From 0 to
Yeah, 0 to infinity. Okay, which here again, this is why we can't have negatives inside of our logarithm, because we have that asymptote there at x equals 0, blocking us from being able to do that. It's not a part of the domain. Okay. All right, so how do we graph one if there are any shifts? Go ahead and write this one down. It's log base 3 of x plus 1 in parentheses and then a plus 2 at the end. I'll say it again. It is log base 3 of the quantity x plus 1 and then after plus 2. There it is. Look at that. Okay. So just like with any other graph, I want you to think of the parent function first. So take away any shifts, stretches, reflections, anything like that, and our parent function is just log base 3 of x. Okay? Well, that is what we graphed before on the previous slide, but I will remind you what I want is for you to plug in negative 1, 0, 1 to the y column, and then your x column becomes the 1 over a, 1, a. Okay? I'm hoping that all of these graphs you've seen that pattern of what that y column looks like for the exponentials, and now that's becoming our x column for the logarithm graphs. Okay? So now, let's talk about what this is going to look like. Okay? Kiana, can you tell me what this 1 and 2 will be doing to our graph? So left 1 and up 2, okay? So this 1/3 negative 1 is going to shift left 1 and up 2. So it becomes negative 2/3, 1. The coordinate 1, 0, we need to shift left 1 and up 2. So it becomes the coordinate 0, 2. The coordinate 3, 1, we're going to shift left 1 and up 2. So it becomes 2, 3.
Can you explain the 2/3?
Yeah. So we're at 1/3 and we have to move left 1. So if we subtract 1, we're at negative 2/3. So we're basically subtracting 1 from all of our x's if we're moving to the left. Okay? Now, is our asymptote still at x equals 0? Where is it?
Y equals
X equals negative 1 is where our asymptote would be. It's usually at x equals 0, while horizontal shift is going to affect our vertical line. Everybody, what's our range?
all
All real numbers. Okay.
There's no hole in that.
Nope, no hole. Our domain, Jade, what would it be?
Negative 1 to infinity.
Excellent. Negative 1 to infinity. I have one more graph I want to talk about. I feel like it is my duty to go through a natural logarithmic graph just to talk about that parent function. Okay, and then I have an algebraic example and then we're done. Okay, I even may show you a video if you can bear with me. Okay, I'm like, you guys are like dropping like flies. Like, I don't know if it's the rainy weather and it's after lunch, I don't know, but our enthusiasm has definitely fallen. So let's graph y equals natural log of x. Okay, let's talk about what this looks like. It is a parent graph, so I'm just going to go ahead and fill in my x equals 0 asymptote. Okay. I will point out too that on the quiz on Friday, I will have you label asymptotes like I'll ask you for them, and you need to know which graph has a vertical asymptote and which one has a horizontal asymptote. It's only one or the other in these graphs. Okay. Since it's a logarithmic graph and we're talking about the parent function, negative 1, 0, 1 is going to go in the y column. Okay. And then if we think about our x values, we have what the y values were for exponential, right? We just flipped them. So we know that E is like 2.7-ish, so 2.7110. There's our natural logarithmic graph, okay? Just like yesterday with the e to the x graphs, you're probably going to need your calculator to help you approximate any of the transformations because we're dealing with an irrational number, but I still want you to do as much as you can without your graphing calculator because you do not get a calculator to graph on Friday. Yes. Yes. Jade, what is the domain for the natural log? Yep. And just like any other logarithm, our range is all real numbers. Okay? Good question. Okay. There is something that I want to come back to here. I need to come back to this graph right here. What if I asked you for an x-intercept? How do we find an x-intercept? We plug 0 in for y. So 0 equals log base 3 of the x plus 1 plus 2 minus 2 plus 2. Okay. How do I solve for my x-intercept here?
Oh, you do the opposite equation.
Not quite yet. What do we have to do first? Let's subtract 2 first. And then we did all of that work on how to rewrite logarithms. Okay? We have base 3 to the negative 2 power equals x plus 1. Think about what a negative exponent means. What is 3 squared? 9. 3 to the negative second would be 1/9. So our 0, we would subtract 1, is negative 8/9. So our x-intercept would be negative 8/9, 0. Okay. That's a little glimpse into what we will be working with next week. But we have the skills to do it. Yes?
For that framework, can you just explain that?
Yeah. So typically in our parent function, we have a vertical asymptote of x equals 0, right? Well, since we have a shift to the left one, then our asymptote gets shifted left. We don't have horizontal asymptotes in logarithms. We only have vertical. And we only have horizontal and exponential. So it's either one or the other. Does that make sense? Exponentials have horizontals and logarithms have vertical. Is that clear? Okay. Last thing before I let you pack up, we need to talk about how we would solve one of these equations. So go ahead and write it down. What's true about the bases of our logarithms? They're the same. What's true about our two logarithms? They are equal. So if we have equality and we have the same base, what's true about the insides? Then the insides are equal. It's one of those things. Sometimes it seems too simple, right? So what do we have? We subtract this over x equals -2. Is that a question?
So how do we get the same power? Like, do you have an example of getting the same power like the word?
They just, right now, no, they're just going to have to be the same base. Like, I'm going to have to give them to you as the same base. Like, you're not going to get one that's not. Does that make sense? Okay. All right. So, let me go ahead and, okay, so